a quick 9702 AS level physics deformation revision. Okay, so for starters, you have to understand that for deformation, there is very few things that you actually have to know, and they involve just these 5 things that you have to understand. For this part, we're only going to cover up these 3 things that are graphs, terms, and formulae. So without wasting any second, let's just start on with our terms. So here are some terms that you are going to have to know for your 9702 AS level deformation, starting off strong with Hooke's law. Okay, so Hooke's law essentially is just that Hooke's law states that force is directly proportional to extension provided that the limit of proportionality is not crossed. And when we state that two things are directly proportional to each other, we always introduce a constant, and that will be in this scenario K, which is your spring constant. Okay, moving on towards elasticity, it is actually kind of the opposite of what a lot of students tend to think that it is. Elasticity essentially means that when a applied force on an object is removed, how easily can it regain back its original shape? So, for example, if you compare a rubber band and a steel wire, the more elastic of the two would definitely be a steel wire, and that is why we say that elasticity refers to the rigidness of a material. Okay, moving on, we have extension and compression. These are essentially the changes that are made to the length of an object, not the final product itself, but it is the change that is observed. Moving on, we have elastic potential energy, which is essentially the the elastic potential energy is the energy that is possessed by an elastic body due to its deformation. Okay, then we have stress, which is the internal pressure of any object, and it is denoted by a force upon area. We have strain, which is just the ratio of the extension over the unstretched length. The Young's modulus, which you obtain after you divide these two quantities together, which is stress over the strain. Then you have the strain energy density, which you actually obtain after you divide the elastic potential energy or strain energy with the volume of the object. Now, here is something that is known as tensile deformation or compressive deformation. What this essentially means is deformation is the change in shape or size of an object. So, when you apply a tension or a compression on an object, the change in shape or size of that object is known as the tensile deformation. Plastic deformation, on the other hand, is you stretch an object or you compress an object and you remove the force on the object. This object will not return back to its original length. And that means that it has deformed plastically. For elastic deformation, it is quite the opposite. That means after an applied force on an object is removed, the object returns back to its original length. Then we have limit of proportionality, which is the limit up to which Hooke's law, which states that force is directly proportional to extension, is obeyed. Then we have ultimate tensile stress, which is the maximum stress that an object endure before failure. Okay, then we have breaking point, which just means that your object has broke, okay, and the spring constant, which is just the force divided by unit extension. Okay, now that we're done with these terms, let's move on towards the formulae, which you have to understand how a lot of these formulas are derived and how there are other ways to write the same formula. First of all is our very easy peasy Hooke's law formula. Then we have the formula of stress, the formula of strain, the Young modulus formula, and you have to understand how you can write this in different ways because that will be tested in your examination. Then we have the elastic potential energy formula, which is half Fx, and then we have the strain energy density formula, and the spring constant, and another way to write the spring constant. And next we have graphs, and this is important in the sense that you have to know there are less graphs, but you have to know the working behind each and every graph, so it's very easy for you to kind of grasp the MCQs because this would help you out. For every single graph, you have to know what the area under the graph represents, what the gradient represents, and you have to understand that if your graphs are not in SI units, you have to convert them to it, and you have to also understand the way the axes are placed. First graph is our very easy peasy force extension graph. That is the most, I guess, the common graph that you will see in this chapter a lot, and you have to know that the gradient represents the spring constant. However, the area under the graph is a little complicated because you can say that it represents the elastic potential energy, but the way it does so, we will study over here. First of all, let's move on towards the very easy stress over strain graph, the gradient of which gives you the value of Young's modulus, but the area under this graph gives you strain energy density. And another way to write strain energy density that can be tested in your MCQ paper is going to be half into stress into strain, because that is essentially the area of this triangular shaped graph that you have over here, right? Okay, moving on from this, we have to now understand how we can represent the elastic potential energy through a force and extension graph. Right, so this is a classic loading unloading graph that basically shows this part is the unloading and this part is unloading, and here you can see that this object has undergone plastic deformation because when the applied force is removed, the object is not returning back to its original shape. Now if you consider the area between these two loading and unloading parts, you will get the energy loss or the energy that is dissipated. Okay, now If you consider the area under the unloading graph, this shows you the energy that is stored in the spring or the potential energy of that spring. If you add these two areas up, you get what is known as the work done in stretching the spring, or the total elastic potential energy of the spring, or just the total work done. And if you want to find out the net work done, you will simply get this value. Okay, now this is it for the deformation revision part 1, and come to part 2 to get done with these two things and solidify your AS level deformation topic. Thank you guys, and take care.